Hello, my name is Shahriari, and this is a lecture based on my book, Retrolinear. The title of this lecture is Expansion Theorem and the 2 out of 3 theorem. We want to continue asking the question of how do we construct a basis for a vector space. What we have seen in the previous lecture was something called the contraction theorem. You start big, you start with a spanning set, and then throw out elements to bring it down to a basis. And the contraction theorem told us exactly how to do that. Now, the dual approach, the one that we will be talking about today, is start small. Start with a linearly independent set and expand it. Add elements to it until you get to a basis. In addition to the expansion theorem, we'll learn how to leverage the dimension to cut down on our work. And that's where the 2 out of 3 theorem comes in. And an important fact that we will use that we proved in the previous lecture is that for finite dimensional vector spaces, all bases have the same size. And that size is called the dimension of the vector space. Let's start with the expansion theorem. It says that if you start with a finite dimensional vector space, that means that a vector space that has a finite basis. You walk into a vector space, you want to construct a basis, but you've got a bunch of vectors that you really like. Now, if those vectors happen to be linearly dependent, well, you're out of luck. You can't make a basis out of vectors that are linearly dependent. But if you have a bunch of vectors that are linearly independent, they might not be a basis, but you can always find yourself a basis that includes every element of S. In other words, you can expand S, your set of linearly independent vectors, by adding appropriate other elements to the set to get a basis for V. Another way of thinking about that is that if you have a linearly independent set of vectors and you want a basis that contains them, you can come up with other things to make it a basis. You never have to say sorry and say, well, look, you guys are good, linearly independent, but I can't make a basis out of you. I have to throw some of you out, start from scratch. That never happens in a vector space. If you have a linearly independent set, you can expand and include other vectors in the set to make it a basis. So why is that true? So we have a vector space of finite dimension, and we have a linearly independent set called S. Let's say that its elements are W1 through Wm, and we want to see what should we add to that. Now, we know that V is finite dimension. Then you know that the set already has a finite basis. Maybe the set V1 through Vn includes some of the W's, but in any case, there's a basis for V, maybe with n elements. Then what are we going to do? We're going to do something similar to things we have done in the past, which is we consider it as expanded set. We took our elements W1, and now we throw in the whole basis. Now, this is much more elements than we had earlier, whether in S or in the basis. And in particular, we are going to put these elements in this particular order. We're going to put the W's first, then the V's. Now, what can we say about this set? Well, this set still spans V. The reason is that, well, it has a whole basis in it. So of course it spans V. It has way too many elements. It didn't even need any of the W's to span V. But it's also linearly dependent. Why? Well, because any one of those W's can be written as a linear combination of the V's because the V's were basis. But because it's linearly dependent, we can use the method of the contraction theorem and turn it into a basis. We know the span is V, so now we start throwing elements out. One by one and in order, we go through the elements and ask, is the first one the zero vector? Is the next one a linear combination of the ones before? And so on. Now, when we do that, none of the W's are going to be a linear combination of the ones before because S was linearly independent. We knew that W1 through Wm are linearly independent, so none of them gets thrown out. We are going to throw out every element that's a linear combination of the ones before. And when we do that, we also know that when you throw out something that's already a linear combination of other things in your set, especially the ones before, and you throw it away, the span does not change. But by the time we are done at the end, we will have a linearly independent set. W's can't be thrown out since S was linearly independent, but M of the V's will be thrown out. How do I know that M of the V's will be thrown out? Well, because the dimension of this vector space is n. A basis had n elements. All bases are going to have n elements. Have those m elements at the beginning. I have to throw away m other ones at the end so as to the size be n. And the results will be a basis that contains S. So some of the V's will be thrown away. Some of them will stay, but all of the W's are there. And at the end, we'll have a set that still spans V and it's linearly independent, so it's a basis. Therefore, it will be a basis that contains F. The proof is helpful because the proof is also telling us a technique. You have a linearly independent set. How do you expand it to a basis? Well, find yourself some basis and then stick that at the end of your set, and then use the contraction theorem and throw away anything that's a linear combination of the ones before, and at the end you will have a basis. Now we're going to talk about the 2 out of 3 theorems, which is one of my favorites. It's a very nice theorem because it's a very helpful theorem. Let's say we have a vector space whose dimension we already know. The dimension is n. This theorem is not going to be helpful if you run into a subspace, for example, whose dimension you don't yet know. It's only helpful when you already know the dimension of a vector space. If you know the dimension, and the dimension is n, maybe it's 47, maybe it's 5, maybe it's 8. Whatever it is, you know it. And then a set of vectors walks through the door, and you want to check whether or not they're a basis or not. So that's what this theorem is for. S is a set of elements. Are they a basis or not? And this theorem says, here's what you need to do. You need to know, I'm going to give you 3 statements. I'm not saying any of those statements are true, but I'm saying that you should check those statements, but you don't have to check all 3. Just check 2 of them, any 2 you like. The first one is that S has n elements. The second one is that S is linearly independent. The first one is just about the size, how many things are in there. And the last one is that S spans V. As long as 2 of the 3 are true, then S is a basis, and then automatically the other one will be true. So you check 2 of them and you get the third one for free. Out of these 3, the first one, S has n elements, is the easiest one to check. You just count. Are there 47 elements in this set or not? It's pretty easy to do. And then that means that you don't have to check both linear independence and spanning, and that's pretty amazing. Why is this true? Well, remember what we have to do. We have a vector space of dimension n, we have the set S, and we have 3 conditions. The size of S, is it n or not? Is S linearly independent or not? Does span of S equal V? If any of those false, then of course it's not going to be a basis, but we're not interested in that. We're interested in knowing if 2 of them are true, then it's automatically a basis. So what if A and B are true? What if it has n elements and it's linearly independent? We don't know if it spans or not. The size of S is n, that absolute value sign we read as size of S. The size of S is n, and S is linearly independent. How do I prove that S is a basis? I have a linearly independent set, and whenever you have a linearly independent set, you should think of what? The expansion theorem. By the expansion theorem that we just proved earlier, you can expand this set, you can add elements to S, bring other elements in to get a basis. But S already has the right number of elements, and all bases have the same size. If S has n elements already and the dimension of V is n, so if you add any elements and make it a basis, then that means you found a basis with n plus 1, n plus 2 elements. That's not possible. All bases have the same size. Therefore, you can't add any elements, which means that S must have been a basis to begin with. So we're done. S is a basis because you can't add any, because expansion theorem says if you have a linearly independent set, you should be able to make it into a basis. But if you can't add anything, it must have been a basis to begin with. But what if you know the size is n and it spans? Well, now you use the contraction theorem. So you have a set with n elements and the span is V, and you want to show again that's a basis. This time by the contraction theorem, you start with your spanning set, you go through it, you throw away anything that's a linear combination of the ones before, and you get a basis. But how many are you going to throw out? Well, you can't throw out anything because again, the set has the right size. If you throw out anything, you'll get a set of smaller size, and a set of smaller size can't be a basis because all bases have the same size. Again, we can't throw out anything, and that means that S itself must have been a basis. So that's if A and C are true. Well, what about B and C? That means that if S is linearly independent and spans, well, that's the definition of a basis. By definition, S is a basis, and we are done. Now, this 2 out of 3 theorem is remarkable. By the way, this name 2 out of 3 is something that I made up. It's not a common name. Is remarkable because it says that if you know the dimension, then the spanning follows from linear independence. If you know that the dimension and you know the size of your set, if you know it spans, it's linearly independent. And linear independent and spanning were quite different things. And the fact that one follows from the other is pretty amazing. This shows you how important dimension is. This is also not a bad time to think about where this whole project of linear algebra started with. It started with the definition of a general vector space. We had a set V. We didn't know what the elements were. We had addition and scalar multiplication, and we didn't even know what those are. We just knew that they follow certain axioms, and the axioms were sort of weak. They were not really that amazing things. But from that, we have proved things that are not obvious at all. Let's look at an example. Say V is polynomials of degree less than or equal to 3, And let's say these 4 polynomials have walked in: x cubed minus 4x squared plus 5x minus 7, 5x squared plus 3x plus 1, 4x plus 7, and 13x minus 1. And my question is that, is S a basis for V? Prior to 2 out of 3 theorem, I would have to show you that this set spans and is linearly independent. Now I say, well, look, there are 4 elements and P3R has dimension 4. So the number of elements is right. And therefore, all I need to do is check one thing: either linear independence or spanning. I'm going to check linear independence. And to do that, I'm going to write them in a different order: 4x plus 7, 13x minus 1, 5x squared plus 3x plus 1, x cubed minus 4x squared plus 5x minus 7. And then I'm going to say, is this set linearly independent or not? Well, the first one is not 0 vector. The second one is not a multiple of the first one. If you multiply the first one by a scalar, you're not going to get the second one. The third one is not a linear combination of the first two because it has an x squared theorem and those guys don't. And the third one is not a linear combination of the first 3 because it has an x cubed term that the first 3 do not. None of them is a linear combination of the ones before, and I could see that without any calculation, and so it is linearly independent. By 2 out of 3 theorem, because it has 4 elements, it's a basis. I don't have to check spanning. Spanning actually would have been pretty hard to do. Like you would have taken some work to do. Well, I mean, not that hard, but it would have taken some effort to do. I don't need to do that. 2 out of 3 theorems that tells me it's automatically a basis. That's pretty amazing if you ask me. There's a question that I want to address at the end of this series of lectures on dimension theory that I've sidestepped and never asked. Do all vector spaces have a basis? We defined finite dimensional vector spaces as vector spaces that have a finite basis. And then we said that everything else we called infinite dimensional. We never actually had a theorem that said, theorem, V is a vector space, V has a basis, finite or infinite. We never had a theorem like that. And so the question makes itself, do all vector spaces have a basis? This question turns out to be much more complicated than it first meets the eye. You would expect the answer to be yes or no. Pause the video and try to think, what do you think? Do all vector spaces have a basis? Should all vector spaces have a basis? If there's justice in the world, would all vector spaces have a basis? To answer the questions, I have to take a little bit of, say, a few other things. Modern mathematics is developed using the axiomatic system. So that means that we make some axioms that we base everything on, and we say that we're not going to prove those. Those are sort of given things, and then we try to see what follows from them. At the foundation is axioms for set theory. And there's axiom for set theory, and based on those, we, for example, study other things, and then we have axioms for vector spaces, and we study those, for example. Using the usual axioms of set theory, you cannot prove that every vector space has a basis. And by this, I don't mean you personally cannot prove, or I don't know how to prove. I mean, you can actually prove that no one can prove. You can prove that no one can prove that every vector space has a basis. But also, you cannot come up with a counterexample. Again, I don't mean that I can't come up with a counterexample or you can't come up with a counterexample. I mean, you can prove that no one can come up with a counterexample. Now, these are pretty tough proofs, but you can do both of those. You can prove that you cannot prove that every vector space has a basis. You also can prove that no one can come up with a counterexample, meaning that come up with a vector space and prove that that vector space does not have a basis. Well, what does that mean? Well, what that means is that you can take the statement, all vector space have a basis, that statement, as an axiom, if you like. If you don't like that, you can take the opposite. There exist vector spaces with no bases. You can take that as an axiom. Either one of those things can be taken as an additional axiom to the usual axioms of set theory. And if you do that, you get 2 different mathematics depending on which one of these axioms you add on. And both of them will be equally valid. So you'll have 2 different mathematics. In one, all vector spaces have bases. In the other one, there are vector spaces in which that do not have bases. How does that work? Well, just to make sort of make this a little bit more understandable, I will tell you a few more things. Euclid's this whole axiomatic idea goes back to a book by Euclid, although we don't know who Euclid is, or if there was one person or several people, whether or not it was a man or a woman or a group of people and so forth. People usually say Euclid was a Greek mathematician, and by that all they mean is that we believe that he, she, they wrote in Greek, although certainly they were stationed in Alexandria, which is in northern Africa. But this book, Elements, about 300 BCE, builds geometry based on axioms. And in that book, the axioms are meant to be self-evident truths. You start with truths, things that are obvious, and then you build this structure that is going to be all about truths. One of all those axioms are things like are sort of pretty obvious things, actually. One of them is this thing called the fifth postulate, or the parallel postulate, which says that given a point not on a line, not on a straight line, a point outside of a straight line, you can draw exactly a unique line through that point that's parallel to that given line. This one did not seem as obvious. I mean, it's sort of obvious, but it didn't seem as obvious to people as the rest of the axioms. And so for over 2,000 years, mathematicians tried to prove this axiom from the other ones. They did not succeed. Although they did make actually a lot of progress in sort of understanding axiomatic systems, understanding geometry, coming up with other versions of the parallel postulates, but they were not able to use the other axioms to prove this. Then eventually, in the 1830s, in the 19th century, the Russian mathematician Nikolai Lobachevsky and a Hungarian mathematician János Polai independently decided to do something else. They said, well, heck with this axiom. What if we take this axiom out and we put a different axiom in? Put an axiom in that given a point not on a line, there's at least two lines that go through it parallel to the given line, or there are no lines that go through that point and are parallel to this given line. Now, people thought, well, that's crazy. Well, why would you try something that's just not true? But they did this. They built a whole new geometries built on this, and no inconsistency emerged. There was nothing wrong. They were just very different. And in fact, people were able to prove that no inconsistency, if Euclidean geometry works, these geometries also work in the sense that, not in the sense that they are true, but in the sense that there's no inconsistencies and it's a consistent system. And in fact, even though originally this was taught as a kind of a game that people were playing, these non-Euclidean geometries have found much application in modern physics. And since in modern physics one believes that the world is sort of warped, these non-Euclidean geometries are actually much better geometry describing our universe than the Euclidean one is. And this is to say that and because of this whole experience, mathematicians no longer think of axioms as self-evident truths. Rather, they think that we make assumptions and then we see what the consequences of our assumptions are. And the same thing is true with vector spaces. With the usual assumptions of set theory, we cannot prove or disprove whether or not all vector spaces have a basis, but we can take one or the other as an axiom if you want to. Now, if you take the axiom, I mean, most mathematicians would take the axiom that all vector spaces have a basis if they were going to take an axiom. And you might say, well, okay, well, let's take that. And what's wrong with that? There's nothing wrong with that. In fact, that's equivalent to something else that follows from something else called axiom of choice that you could take. But then you get some other things that you might not expect. Like, for example, if you take this as an axiom that all vector spaces have a basis, then it also follows something called the Banach-Tarski paradox, which says that you can take a sphere, a tiny sphere, solid sphere, cut it up into a finite number of pieces, put it back together in a way that's again a solid sphere, and you just took these pieces and moved them and put them together. It's still a solid sphere, still full, but now it has twice the volume as before. So if you believe that, you could start with a tiny atom, do this, and keep doing it, and get to the sum. And now it goes counter to your intuitions about what volume means and what cutting and putting back together means. Those pieces, by the way, are not really easily cut. They are very unusual pieces, but in fact, they can't be cut that easily at all. But that follows from if you end up assuming this axiom of choice, then that will also follow. Okay, so that's the end of this lecture. Hopefully that was a little bit of a mind twister for you at the end, and we'll see you later.